Hello everyone. Today we are going to analyze this beam using Kani's method. Before analyzing, let us see the beam one time. In this beam, there are three spans AB, BC, and CD. Also, we have an overhanging portion DE. In the span AB, we have a point load and uniformly distributed load. In the span BC, there are 2-point loads. In the span CD, there is a point load and a uniformly distributed load. In the overhanging part DE, in the point E, we have a concentrated moment 10 kilonewton meter. It is acting in the clockwise direction. The moment of inertia for AB is 1.8 I. For BC, it is I. For CD, it is 1.6 I. And for DE, it is I. Length of AB is 3 meter. Length of BC is 5 meter. Length of CD is 4 meter. And the overhanging portion is 2 meter. In the point D, we can easily find the final moments because on the right side we have overhanging. In the point E, we have concentrated moment 10 kilonewton meter. It is acting in the clockwise direction. So MDE should be acting in the anti-clockwise direction. So it will be negative, and MDC should be acting in the clockwise direction and it should be positive. The values of MDE and MDC should be equal to this moment 10. Now we are going to find the fixed end moments. First, let us take the span AB. First, let us consider the point load. It is acting in the center. If the point load is acting in the center, the formulas to find the fixed end moments are WL upon 8 and WL upon 8. On the left side, the fixed end moment will be acting in the anti-clockwise direction so that it will be negative. And on the right side, it will be acting in the clockwise direction so that it will be positive. Here W is 16 and L is 3. Now let us take the uniformly distributed load 4 kilonewton per meter. If uniformly distributed load is acting for the full span, the formulas to find the fixed end moments are WL square upon 12 and WL square upon 12. Since this moment is acting in the anti-clockwise direction, it will be negative. Here W is 4 and L is 3. We have to add these two. After adding, we will get minus 9 kilonewton meter. And when we add these two, we will get positive 9 kilonewton meter. Now let us take the span BC. In the span BC, there are two eccentric point loads, 50 kilonewton and 25 kilonewton. If in the fixed beam there is an eccentric point load, the formulas to find the fixed end moments are WAB square upon L square and WA square B upon L square. First, let us take this load. Here W is 50, A is 1 and B is 4. Let us apply them and L is 5. Now let us take this load. Here W is 25, A is 3 and B is 2 and L is 5. After adding these two, we will get minus 44 kilonewton meter, and after adding these two, we will get 26 kilonewton meter. Now let us find the fixed end moments in the span CD. In the span CD, we have a point load and uniformly distributed load. First, let us take the uniformly distributed load. We know the formulas to find the fixed end moments. Here W is 6 and L is 4. Now let us take the eccentric point load. We know the formulas to find the fixed end moments. Here W is 48, A is 1, B is 3 and L is 4. After adding these two, we will get M of CD, and after adding these two, we will get M of DC. We have found the fixed end moments in the span AB, in the span BC, and in the span CD. For DE, we have found the final moment. Let us enter that. In the point E, there is a clockwise movement 10. This movement can be taken as the movement in ED. Since it is acting in the clockwise direction, it is positive. We know the final movement for DC, which is 10. So we have to make DC 10. For DC, the fixed end moment is 17. When we add minus 7 with 17, we will get 10. From DC, we have to give carry over to CD. Minus 7 by 2, we will get minus 3.5. Now let us find the adjusted fixed end moments. In CD, we have to add these two values. When we add, we will get minus 38.5. In the Kani's method, we have to find the rotation factors. To find the rotation factors, we have to calculate the stiffness. Let us see the formulas to find the stiffness. If the fare end is fixed, the formula is 4EI upon L. If the fare end is hinged or with roller support, the formula is 3EI upon L. And if the fare end is continuous, the formula is 4EI upon L. In the joint B, first let us find the stiffness for BA. For that, from the joint B, we have to look at the point A. In the point A, there is a fixed support. If the parent is fixed, the formula is 4EI upon L. For BA, the moment of inertia is 1.8I. So instead of I, we have to apply 1.8I. Length of BA is 3. Let us apply that. For the stiffness of BA, we will get 2.4 EI. Now let us find the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous because after the point C, there is a span CD. If the parent is continuous, the formula is 4EI upon L. Length of BC is 5. Let us apply that. For the stiffness of BC, we will get 0.8 EI. Now let us find the stiffness in the joint C. First, let us find the stiffness for CB. The stiffness for BC and CB will be same. Now let us find the stiffness for CD. For that, from the point C, we have to look at the point D. In the point D, there is a hinged support. If the fare end is hinged, the formula is 3EI upon L. The moment of inertia for CD is 1.6I. So instead of I, we have to apply 1.6I. Length of CD is 4. For the stiffness of CD, we will get 1.2 EI. We should not consider the point D as continuous because after the point D, we have only overhanging. That is why we have applied the formula 3EI upon L. Let us find sigma k. We have to add these two values. After adding, we will get 3.2 EI. Then we have to add these two values. After adding, we will get 2 EI. Now, using this formula, we can find the rotation factors. In the Kani's method, we have to make boxes in the joints. No need to make in the joint D because in the joint D we have already found the final movements. Now let us enter the fixed end movements. In the joints we have to add the fixed end movements. When we add these two values we will get minus 35. And when we add these two values, we will get minus 12.5. Now let us enter the rotation factors. In the Kani's method, in the joins, we have to find the rotation contributions. Using this formula, we can find the rotation contributions. Now let us find the rotation contributions in the joint B. For the joint B, the fair ends are the point A and the point C. In the point A, the rotation contribution is 0 because it is a fixed end. In the point C, initially M dash CB will be 0. So for the summation of rotation contributions at a fair end, we have 0 plus 0. The summation of fixed end moment is minus 35. The rotation factor for BA is minus 0.375 and for BC it is minus 0.125. When we calculate this, we will get M dash BA and M dash BC. Let us enter both of them. Now let us find the rotation contributions in the joint C. For the joint C, the fair ends are the point B and the point D. In the point B, we have the rotation contribution 4.375 and in the point D, the rotation contribution is 0 because we have released DC. So for the summation of rotation contributions at a fair end, we have 4.375 plus 0. The summation of fixed end moment is minus 12.5. Then let us enter the rotation factors. After calculating these, we will get M dash CB and M dash CD. Let us enter both of them. We have finished the first iteration. Now let us start the second iteration. Let us find M dash BA and M dash BC. We know that in the point A, the rotation contribution is 0. In the point C, we have the rotation contribution 1.625. So for the summation of rotation contributions at fair end, we have 0 plus 1.625. The summation of fixed end moment is minus 35. Then let us apply the rotation factors. Finally, for M dash BA and M dash BC, we will get these. Let us enter both of them. Now let us find M dash CB and M dash CD. In the point B, we have the latest rotation contribution 4.172 and in the point D, the rotation contribution is 0. So for the summation of rotation contributions at fair end, we have 4.172 plus 0. The summation of fixed end moment is minus 12.5. Then let us enter the rotation factors. After the calculation, we will get M dash CB and M dash CD. Let us enter both of them. We have finished the second iteration. Let us start the third iteration. Let us find M dash BA and M dash BC. We know that the rotation contribution in the point A is 0. The latest rotation contribution in the point C is 1.666. Then let us enter the summation of fixed end moment. Then let us apply the rotation factors. After the calculation, we will get M dash BA and M dash BC. Let us enter both of them. Now let us find M dash CB and M dash CD. In the point B, we have the latest rotation contribution 4.167. The summation of fixed end moment is minus 12.5. Then let us enter the rotation factors. After the calculation, we will get M dash CB and M dash CD. Let us enter both of them. In the second and third iterations, we have got approximately same values. So we can stop in the third iteration and find the final moments. Now let us make a table. In the table, first let us enter all of the members. Then let us enter the fixed end moments. Then let us enter 2 into near end rotation contributions. For AB, the near end rotation contribution is 0. For BA, it is 12.5. For BC, it is 4.167. For CB, it is 1.667. And for CD, it is 2.5. Then, using the arrows, we can enter the fair end rotation contributions. Then we have to add these three. After adding, we are getting the final movements. For DC, we have already found the final movement. Now we are going to find the vertical reactions. First, let us take the span AB and find the vertical reactions. In the span AB, we have two movements, MAB, which is acting in the clockwise direction, MBA, which is also acting in the clockwise direction. By taking moment about B, we can find RA, and by applying this rule, we can find RB1. Now let us take the span BC and find the reactions RB2 and RC1. In this span, there are two movements, MBC, which is acting in the anti-clockwise direction, and MCB, which is acting in the clockwise direction. By taking moment about C, we can find RB2, and by applying this rule, we can find RC1. Now let us take CD and DE together and find the reactions RC2 and RD. No need to consider these two movements because both of them will get eliminated. We have to consider this movement which is acting in the anti-clockwise direction and this movement which is acting in the clockwise direction. By taking moment about D, we can find RC2, and then by applying this rule, we can find RD. Let us find RB by adding RB1 and RB2 so that for RB we will get 76.6 kN. To find RC, we have to add RC1 and RC2. When we add both of them, we will get 78.775 kN. Here you can see the shear force diagram. Now we are going to draw the bending moment diagram. First, let us find the bending moment in the ends and in the joints. In the point A, we have sagging bending moment so that it will be positive. In the joint B, we have hogging bending moment so that it will be negative. In the joint C, we have hogging bending moment so that it will be negative. In the joint D, we have hogging bending moment so that it will be negative. Finally, in the point E also, we have hogging bending moment so that it will be negative. Using the end moments and the reactions, we can find the moments under the point loads. We can use right hand side rule. Clockwise will be positive and anti-clockwise will be negative. Let us take the span AB and find the moment under the 16 kN point load. This moment is acting in the clockwise direction so that it will be positive. This reaction is acting in the clockwise direction so that it will be positive and the distance is 1.5. The UDL is acting in the anti-clockwise direction so that it will be negative. With the UDL, we have to multiply the distance and distance by 2. After the calculation, we will get 1.25 kN meter. In the similar way, we can find the moment under the 50 kN point load, 25 kN point load in the span BC. In the span CD, we can find the moment under the 48 kN point load. Here you can see the bending moment diagram. Alternatively, we can draw the bending moment diagram by superposition method. In this method, first we have to consider every span as a separated simply supported beam. First, let us take the span AB and assume that it is a separate simply supported beam. We need to find the reactions RA and RB. Since we have symmetrical loading, we have to add the total load and then divide that by 2. When we do that, we will get RA and RB. Now, using the right hand side rule, we can find the bending moment under the 16 kN point load, which is 16.5 kN meter. Now let us take the span BC and find the reactions RB and RC. Let us draw the bending moment diagram. 50 into 1 we will get 50 and 25 into 2 we will get 50. Now let us take the span CD and find the reaction RC, and then we can draw the bending moment diagram. Now using the end moments we can draw the end moment diagram. Then we can combine the simply supported moment diagram and the end moment diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.